Alright, kiddos, it is time for the last section of Unit 8. We are working on properties of buffers. I am back at school, so it's this setup. Sorry if you don't like it. Alright, so we're going to scoot through some of these really quick. I took the problems out of the PowerPoint because I just want to work some problems here on the paper. But they're going to be very repetitive. Alright, so make sure you understand what a buffer is. So a buffer is a solution that contains a conjugate acid-base pair of a weak acid and its conjugate base, or a strong acid, or a weak base and its conjugate acid. Okay, so it's a weak acid or a weak base and its conjugate. That is what a buffer is. Many times you're asked to just solve for the pH of this buffer, and then sometimes you're asked to solve for the pH if they change it by adding something, and you have to think about what's going on and what they're adding. So if they just give you a buffer solution, then you need to do Henderson-Hasselbalch to solve this problem. If they're giving you a buffer solution and then they are adding either some other acid or some base, then you have to do a Rice table before you can do the Henderson-Hasselbalch. Okay? And just so you know, for the Henderson-Hasselbalch, the equation is like this. It's pH equals the pKa plus the log over the concentration of the acid and over the conjugate bases on top. And if you do the pOH equals the pKb plus the log, you have the base on the bottom, and you have the conjugate acid on the top. So the conjugate goes on the top, and then the acid or the base, depending on if you're dealing with an acid or a base, goes on the bottom. Okay? So make sure you know that. That's important because you kind of move stuff around, and you're going to see that when we work a couple of problems in a second. Okay. So what we're going to do is go through this really quick, figuring out who the conjugate acids and or bases are to these particular practice problems. All right, so we have HPO4 2 minus, H3O plus, F minus, and HCO3. And then we want to know what would be the conjugate base or what would be the conjugate acid. Okay, well, if we're solving for that, then let's just do the conjugate acid side first, okay? So if it's a conjugate, we need to know who the conjugate acid is. That means that it's acting as a base. What do bases do? Bases accept protons. All right, so if I can accept a proton as a base, is this one going to accept a proton? And it definitely can. It can become H2PO4 minus 1. Make sure you adjust the charge. If you get that wrong, you lose a point. H3O plus is not going to accept a proton. Not going to have a conjugate acid. F minus definitely will accept a proton. And then HCO3, it can, that should be a minus 1. Okay, yes, I see it on this PowerPoint now. I didn't write it down. That's a bicarbonate. We'll make carbonic acid. So there you go. So that's the conjugate acids for those particular substances. Now, if we want to know what the conjugate bases are, then that means that these guys would have to act as an acid. What do acids do? They donate a proton. So will this one donate a proton? Sure. There it is. Will this one donate a proton? Absolutely. Will this one donate a proton? No. Doesn't have one to give. Can the last one donate a proton? And the answer is for sure. Okay, so these would be the conjugate bases of these substances if it were acting as an acid. Now, of these substances, which ones are amphoteric or amphiprotic, meaning they can act as both an acid or a base? And the answer is this one, the biphosphate, and the bicarbonate. These two are amphiprotic. or amphoteric because they acted as both an acid and they can also act as a base. So that's really good to know and be aware of. So that's just like good to know information. Definitely could be asked that question on a test. All right, so let's work some Henderson-Hasselbalch equations. I'm going to go through a couple slides, and then we're just going to work some problems. Those of you that know me know I hate doing math on a PowerPoint, so I deleted the PowerPoint slides. I'm just going to work them here. I prefer that anyway. All right, so what we're doing with this is your Henderson-Hasselbalch equation. So pH equals the pKa plus the log of the base over the acid. So you have your acid here, and this is your conjugate base on top. The acid here, because this is an acid, so pay attention to that. Now, when we prepare a buffer, the best thing to do to prepare a buffer is where the concentration of your acid and your base are equal, because when they are, then that means the pH equals the pKa, and that's like right smack dab in the middle of an excellent buffer region, which we'll talk about that right here. So for this particular acid, which is acetic acid, when you take the negative log of the K value, which is 1.8 times 10 to the negative 5, you get 4.76. So that's the pH of the pKa. And so at 4.76 pH, this is like the midpoint in a titration is where it should be, and this is the perfect buffer. Now, a buffering region means that it doesn't have to be just at 4.76 where this will act as a buffer. It's going to act as a buffer anywhere from plus or minus 1. So plus or minus 1 on the pH scale or the pKa, either way, because of the same number. Plus or minus 1 will give you what is called the buffering range. So if it's anywhere from 3.76 to 5.76, this blue area is our range. So 3.76 starts at about here, so at about 0.1 hydroxide equivalents. I don't know what they used, milliliters or what, but whatever the 0.1 equivalents all the way over to around 0.9, this whole region here is the buffer region. Okay, so that's the main point of understanding that there's a region. It's not just one location. All right, before we go into 10, I want to work some problems. Okay, so let's do some math. Yay! Here we go. We have, number 1, a buffer. And our buffer is, let me find this problem. Okay, they gave us moles, which we can use moles. That's fine. So I have 2 moles of acetic acid and 2 moles of sodium acetate. All right, and it's in 1 liter of water. So that means, oh, that's very blurry. Let me fix that. Okay, so that means that moles and molarity are the same because it's in one liter. All right, so first things first, put the brakes on. Let's go calculate really quick what is the pH of this buffer. And let me actually back that up just a second. Is this a buffer? Well, yes, let's identify it. First of all, this is an acid. What kind of acid? Give me an adjective. It's a weak one. Why? Because it's not one of the 6 strong, right? And then this is an ionic compound, also known as a salt. But is this the salt of this acid? And you're looking at its conjugate, which is this acetate ion. Acetate here, acetate here. Yes, this is a buffer. Check. This is a buffer solution. So when I'm in the buffer, there we go. So buffer solution, SOLN, sorry. That means I can calculate the pH by using Henderson-Hasselbalch. So pH equals the pKa plus the log. Acid goes on the bottom. The what should be HA, and the conjugate base goes on top. That's an H. Okay, so let's calculate. Now this is acetic acid, and its its Ka is 1.8 times 10 to the negative 5. So if I want to find out what is the pKa, then I'm going to take the negative log of 1.8 second EE negative 5. Okay, so I get this big long number. I have 3 sig figs here, 3 sig figs here, and assume that's 1.00 liters because it is on my problem. I just didn't write it down. So I have 3 sig figs. So this would be 4.745 because that's 3 sig figs because it's 447. So 4.745 is my pKa plus the log. Now, the concentration of the conjugate base, which is acetate, is 2 molar divided by 2 molar, so that's 1. And if you guys have forgotten, the log of 1 is 0. So that means that the pH equals the pKa. So the pH is simply 4.745. Okay, that's one thing they can ask you to do. You can all do that. That's totally doable. Now, and you can do this next part too, so don't freak out. But now, we're going to take this same buffer, but now we're going to add 0.0100, so we're keeping our sig figs consistent, moles of NaOH. It's going to react, and they typically tell you that there's no change in volume. So you're still dealing with 1 liter, which makes life a little bit easier, but they tell you that, so when they tell you, just go with it, okay? They're testing you to see if you can handle the math. So I don't care about sodium. It's out because it's going to always be floating around, but I do care about this OH minus. Now, who is this OH minus going to react with between this and this? Because remember, sodium's out. So I have acetate or I have acetic acid. Well, OH is a base. It accepts a proton. Only one of these has a proton that it can donate, and it's that one. So I have to rewrite my equation to where it makes sense. I have my acetic acid. Oh my goodness, my acetic acid plus I had it right the first time. OH equilibrium, and then I'm going to have my acetate. C2H3O2, I will get it together, I promise, plus H2O. And H2Os are liquid. Now, I have 2 molar of this, 2 molar of this, that doesn't matter, and I have 0.0100 molar of this. And you're like, well, there's not a 0. How do I figure this out? Well, in this case, there's such a small amount of this OH that's present compared to these others. It's such a small amount. This is my limiting reactant. This will react to completion. So it will be gone. And be gone means that I will use it all up. So the equilibrium is going to shift that way. So I will subtract 0.0100 from the reactant side, and then I will add it on the product side. So this becomes 1.99. And this becomes 2.01. I still plug into the same Henderson-Hasselbalch equation. So the pH equals the pKa plus the log, acid on the bottom, and the conjugate base on top. All right, and so I'm plugging in. I already know what the log of my pKa is, so I'm not going to calculate that again. It is 4.745 plus the log. All right, who is my conjugate base? This is my conjugate base. All right, so it's 2.01 over the acid, which is 1.99. Now, this ratio is greater than 1. It's almost 1, but it's not exactly 1. It's a little bit greater than 1. So when I take the log of this, I should have a positive number. All right, so let's see. 2.01 divided by 1.99. Take the log of that number, and it is a positive number. It's almost 0, but not quite, plus 4.745. And I get that my pH is equal to 4.7 sig figs are still 3.49. Sorry, people are coming in and out of my classroom. So let's think about this for a second. We added hydroxide. We added a base. So if we add a base, we expect our pH to increase. So did it increase from here to here? Well, technically yes, right? But in the thousandths place, did it increase a lot? No, it didn't increase a lot. Why? Why not? Because this is a buffer. And what do buffers do? They resist change in the pH. So because this is a buffer, did it increase by just a tiny bit? Yes. Depending on what your sig figs were, it might not have even increased by any, right? Technically, if we had had two sig figs, it would have been 4.75 and 4.75. And so you would have been like, no, it didn't change. But we do notice it does actually change a little bit, but that's because the pH is just ever so slightly, we have 3 sig figs, and it just ever so slightly increases with the addition of that OH minus. All right, so now let's do another one. So let's take the same initial buffer, so this up here. So we have acetic acid and we have acetate, 2 molar of each. Let's take the same original buffer, and then now, so this is scenario 2, scenario 3. Now what we're going to do is we are going to add, let's see, 0.0100 moles of HCl. Okay, well, HCl is just like the Na. I don't care about it. It means nothing to me. That means I'm adding this much H+. So think about what you've got going on here. I have this guy, my acid, and I have this guy, my conjugate base. Who is going to interact with this H+? Not this, because he already has his H. This one, right? So acetate plus H plus is going to give me HC2H3O2. That's what I get when those two interact together. All right, so I get this. All right, perfect. So now I know that this was 2 molar and this was 2 molar. Technically, it had 3 sig figs. And I know that this is going to be no change in volume and all of that. So the moles is the same as the molarity, 0.0100. Now, again, limiting reactant. So the addition of this acid, this is my limiting reactant problem right here. This is going to all be gone because there's not very much of it anyway. It's going to all be gone. So this is going to be 0. That means on my reactant side, 0.100, and on my product side, okay, and so I get 1.99 on acetate, essentially 0 on that, and I get 2.01 on the acid. Well, I'm still solving for the pH. I still have a weak acid, so my formula is still the pH equals the pKa plus the log of the concentration of the conjugate base over the concentration of the acid. I want you to write it out because it helps you talk yourself through what the heck is going on. So the pH equals the pKa, which is 4.745, plus the log. Now, freeze, put the brakes on. What's going on here? Who is the acid in this? And the acid in this scenario is this. This is the weak acid. It's the acetic acid. He's 2.01. That's my denominator. And then who's the conjugate base of this acid? That's the acetate, 1.99. It's almost a ratio of 1, but it's a little less than 1. If it's a little less than 1, then that's going to make this a negative number when I take the log of it, so it should subtract from that number. Let's see. 1.99, oopsie, there we go. All right, it's negative, 0.0043, whatever. All right, and we're going to sum that with 4.745. And I get 4, again, we're going to work with 3 sig figs. So that's going to be 4.745 3.741 is my pH. So, zoom out for a sec. This is the buffer pH, the pH of the buffer, where the concentration of the acids and the acid and the conjugate are the same. So the pH was the pKa. That's that. It was 4.745. I added a base. It increased a tiny little bit, but not much. I added an acid. The pH went down just a tiny little bit. And does that make sense? Yes. Number one, it makes sense that it went down. If it went up, you did something wrong. And only changed a tiny little bit. And again, depending on sig figs, it could have not changed at all. So it just has a tiny little change only because it's a buffer, and we're in the buffer region. Because remember, this guy has a buffer region of, if this is my pH equals my pKa, his buffer region is from 3.745 to 5.745. So we are smack dab in the middle of it, and it's going to be resisting that change to the pH for quite some time. All right, so buffer solutions are usually prepared from the weak acid and or base and its salt. So two important characteristics of a buffered solution are its buffering capacity and its pH range. So I just mentioned the range for this, so plus or minus 1. So understand that you get plus or minus 1 on that pH scale or on the pKa scale in order for what's considered a buffer zone. That's the capacity. It's a buffer from 3.745 to 5.745. That's the capacity. And so that's the main thing that you need to know about that. So this one, so if we change the concentration of the buffer mixture, the pH is 4.76, so this one is 4.76, would be obtained from, this is acetic acid and acetate ion, so these are the organic names versus what we tend to use in AP, acetic acid and acetate, when you have the concentration of the acid equals the concentration of the base. Here's the point. We have a 1 molar acetic acid and 1 molar acetate solution, buffer solution, and then we have a 0.001 molar and 0.001 molar acetic acid and acetate solution. Both of them have the concentrations of the acid and the base that are the same, which means both of them have a pH of 4.76 at the midpoint. Okay, so that's their that's where their, the middle of their buffer region is the same. But if you do some calculations with these, you'll find that the 1 molar concentration has the ability to respond to the addition of either acids or bases more than the weaker concentration. So the weaker concentration doesn't have as many, in this case it's an acid, so it doesn't have as many H pluses floating around that will be able to attack the OH minuses that come in. So the higher concentration the buffer is, the higher the buffering capacity. So it's able to resist change more. So the 1 molar is a stronger buffer. It's a stronger concentration. It's a stronger buffer. Now I've told you guys before, strong always wins in chemistry. Strong wins. So the stronger the weak acid and its conjugate, and or weak base and its conjugate, the stronger the buffer is, which means its capacity to resist that change is going to be greater. And the weaker the weak acids and bases are, then that's where you're going to end up with weaker situations. Okay, so if we are going to change the composition of the buffering mixture, if your acid is greater than your base, then that means you have more H pluses floating around. That means you are able to deal with these OH minuses because you have an H plus that can handle this OH minus. So the OH minus is invading the buffer zone, and the H plus is attacking it and turning it into water. So it's out of here, and it is no longer going to affect the pH anymore. And so that's the whole point, or it won't affect the pH quite as much. And that's the whole point of what a buffer does, is it is resisting that change. So this is talking about that. Now, if your base is greater than your acid, then that means you have OH minuses floating around in excess, and they are able to address the invasion of any H pluses that are dropped in there. So if an H plus pops up, OH minus is like on it, and it will react with it and make water, and it really reduces the reaction to the change. Okay, I'm actually going to do a couple other different problems than those two. So I have those you guys have those notes, so I'm just going to I brought this because you guys have a copy of this. Use this. Okay? This helps. So make sure you use this, all the little details, the abbreviations, the formulas, what to do when. So you guys have a copy of this in your notes, so use it while you're studying, okay? It'll help you. All right, so let's work a couple more problems, and then we will be done, because they're very repetitive. Once you kind of get the hang of it, it's not that bad. This is probably one of the hardest things we do in AP Chemistry, in my opinion. You might think different, which is fine. If it's easy, it's because I'm an amazing teacher. Just kidding. Not kidding. All right. So, don't forget your buffer region is plus or minus 1 on the pH scale. All right, so let's see. I have some sample problems here. I've got them written right over here, so I'm going to pull out the stuff that we want to have. Considering the following buffer system composed of acetic acid and sodium acetate. We like this one. All right, they're telling me my pKa is 4.76 to use on this one. All right, 4.76 is 2 sig figs. Okay, so for this one, let me look at what I just worked so I can make sure I am not redoing some of the ones that I've already done. Okay, they're similar, but they're not exactly the same. Okay, so for our first one, we have buffer A. We have 0.1 molar of each. So I have 0.1 molar of the acetic acid, and I have 0.1 molar of the sodium acetate. So I have 0.100 molar of each. Okay. So again, if I want to know what the pH is of this system, if they're both the same concentration, you don't even have to write it out anymore, because you know that the pH is equal to the pKa, which is equal to 4.76, because the ratio of 0.1 divided by 0.1 is 1, and when I take the log of that, it's just going to be 0. So this is where I'm at. So now we are going to add 0.0500 moles of NaOH. All right, so I'm adding this NaOH to my buffer solution, and when I do that, I now need to think about what is happening with who is reacting with whom. All right, so I have this acid and I have this conjugate base. Hold on just one second. Okay, sorry, I'm back. The janitor was coming in and wanted to vacuum, and I was like, no, dude, come back later. Okay, so we're going to add this base. So hopefully you paused and you started doing this yourself and see that you can do it. So I'm adding this base, and this is a 0.1 molar of each one of these. Who is the base reacting with? Is it going to react with the acid, or is it going to react with this conjugate? Because remember, we don't care about sodium. It's going to react with the acid. So I have HC2H3O2 plus hydroxide is at equilibrium, and I end up with acetate over here and water, because this H is going to come over here to this OH and give me water. Don't care about this. I have 0.100, 0.100, and I have 0.05. Again, typically how this works is they will usually tell you there's no volume change, so the concentrations don't change, and then they will usually also indicate somehow that this goes to completion for the hydroxide, so it's a limiting reactant problem. All right, so that means that this is gone, and so I am, oops, there's another 0 in there. Subtracting on the reactant side, adding to the product side. And when I get down to my E side, that means that this is 0.050. This is basically 0. And this is going to be 0.150. Now, Henderson-Hasselbalch doesn't change. Plus the log. This is an acid, so the acid goes on the bottom, and the conjugate goes on top. Okay, and I'm solving for the pH. So let's plug in. My pKa is 4.76. There we go. Plus the log. Go find it. Where is the conjugate base and where is the acid? This is my acid, HA, and this is my conjugate base. So my numerator is 0.15 and 0.05. Now, this ratio is greater than 1. Numerator is bigger, so that means that when I take the log, it should be a positive number. And it is. And I'm going to add it to 4.76. Now, notice this time the pH is a bigger change, 4.24, I see, because we have 2 sig figs there, where our 3 here, but they gave me 2. So it goes up quite a bit, 5.24. Now make sure that makes sense. I added a base. Does it make sense that my pH went up? And the answer is yes, it did. It does make perfect sense. Okay, so it makes perfect sense. Now, we're going to do the same thing. So what we're doing is proving what we just talked about on one of the last slides, where we still have the same acetic acid and acetate, but instead of being 0.1 molar, they're 1 molar. All right, so for B, our situation is 1 molar of each. All right, so I have 1 molar of each, and then I'm still going to add 0.050 molar NaOH. So this stays the same. What's changing is the initial concentration of the weak acid and its conjugate. So same reaction. So I have H, C2H3O2 plus hydroxide gives me this. All right, now I have 1 molar, and 0.05 molar, and I don't care about that. Limiting reactant, so subtract it, add it. There we go. I think I got it. All right, so this is 0.95. This is 0, and this is going to be 1.05. Oh, I'm sorry, I'm not on the screen. We're not in class, so you can't tell me, hey, sorry. So what I did was limiting reactant was this one, so I subtracted 0.05 here, so I would have none of it left. Also, I have to subtract from the acetic acid because it is they're both on the reactant side. So if I'm subtracting this one, I got to subtract this one. Adding on the product side, pH equals the pKa, which we already know is 4.76. So I'm going to cut that corner just a little bit. Okay, my acid goes on the bottom, 0.95. And my base goes on top, 1.05, or conjugate base. Okay, so now, still greater than 1, it should still add. So 1.05 plus 0.95. Oh, a plus divided by. Take the log of it, add it to 4.76. Okay, so now my pH is 4.80. So let's compare these real quick. That's the whole point of this. here we are. This is just my buffer solution pH up here. This is, both of them I added 0.05 molar NaOH. But for this one, I added it to 0.1 molar acetic acid and its salt. And for this one, what was different is it was 1 molar acetic acid and its salt. So the big thing that's going on here is that we are proving that who is the better buffer, because the buffer is the item that resists the change in pH, which means the pH stays as close as to the center as possible, which is 4.76. Well, obviously, look at this one. It didn't change by very much at all, right? This one changed a pretty decent amount. Like, you could actually, calculate what was the change in the in the pH for these. But what I really want you to get is that if you were asked to pick, like on a multiple choice or something, which would be a better buffer, you want to pick. Obviously, you need to pick something that is a buffer. Don't pick something that's not. Pick a buffer first. But then if they give you more than one, then you're looking for the higher concentration. Because the higher concentration the buffer, the better the buffer. Because it's a stronger buffer. And so if it's a stronger buffer, then anytime any species comes in to invade, and in this case the hydroxide is invading the buffer, then the stronger the acid in the conjugate pair, the stronger one, this one down here in B, is going to be able to attack those hydroxides much more efficiently and resist the change in the pH. Okay? All right, kiddos, that's it for the end of Unit 8. Have a great time. Bye.